Hi friends, welcome to today's class. Today we'll look at Hooke's law, elastic modulus, and bulk modulus. Elastic modulus is what I call the jamb modulus. Now we are going to be discussing literally the response of materials to the application of forces. How materials try to resist forces applied to them linearly and by volume. So we're going to be looking at that. Now, if you have, for instance, an elastic material, for instance, a spring, fastened to a point. Now, let the initial length of the string be L0. Now you apply a force to the spring. There is an extension, okay, by the application of F. Now, the new length becomes, for instance, call it L. So from this point to this point is changing length. So the application of force has produced an extension from what it was to what we now see it is. Now, changing length, the extension produced as a result of the application of this force F equals final length minus original length. Okay, this changing length usually is positive because the final length usually is bigger than the original length. Now, Hooke's law says if you want large extension, you have to apply large force. So, mathematically it says that the application of force, the applied force varies directly as the extension produces changing L. And so, if you are to put the sign of equality, you put what we call a constant of proportionality in mathematics. Now, Hooke says if you plot, of course, it's been verified experimentally, if you plot a graph of force in Newton against extension in meters, you get a straight line from the origin. Now from this point, we call it, that is 0, number 0. Now let's say, okay, let it be O, an alphabet to P, B, A, here, B, C, and here, this point D. Now from this point, according to this law, of course, if you plot a graph of, if you take the slope of this graph, within the limit of elasticity, it gives us K, constant K, which depends on the nature of the material. Okay. Now, from this point to this point, it's called elastic region. From this point, OB, okay, OB, elastic region. So elastic region. For this point BC is called the plastic region. At this other point is the breaking point. Now point A is called the elastic limit. Proportional limit. It's still proportional limit. Point B is called elastic limit. Beyond, at this point, the material, if you remove the force, applied force, you remove it, the material will still go back to its initial shape. It will return to L0. Okay? Now, point C is called the yielding point. Or yielding limit. Yielding point or limit. What does it mean? If you keep on increasing the force beyond point B, the material gets deformed. gets deformed, but it wouldn't cut. Okay, but if you continue applying the force, we get to point C. Beyond point C, at point D, is called the breaking point. Breaking point. At which point the material gets split into two. Okay, this is exactly what is happening. Now, if we replace, let's keep this formula here, F equals K, change in length, which is Hooke's law. Now, if you replace this spring with something, say a piece of metal of length L, and you apply force to it, so there's an extension. It's L naught L. So the change in length again is L minus L naught. It is positive because L is usually greater than L naught. Now, if you check, you've applied this force. You apply the force to a certain area of the material. The applied force has produced an extension, an elongation of the length. Then if you divide the force by the area to which the force has been applied, you get what we call stress. So stress is defined as force per unit area. Its unit is Newton per meter squared. Okay? Now, if you look at the extension produced as a result of the application of this force, the extension is change in L. If you divide it by the original length, it tells you the response of this material to the applied force. So it tells you change in length literally is measure of deformation. Okay, measure of deformation, but that is in the case of a material that is not elastic, doesn't return back to its former shape. So if it does not return back to its former shape, change in L becomes deformation, it is deformed, because the length has changed. So if you divide the original length by, if you divide the change in length by the original length, it tells you how the response, how deformed it is. Now, we call it strain, which is a measure of the response of, the material to the application of force. This is stress, this is strain. Now, there is an expression relating the two. We call it elastic modulus or Young's modulus. Elastic modulus. Now, E, let's denote this by E. E equals stress over strain. Okay? So we have stress as force per unit area divided by change in length over original length. Okay? Now, if we make change in length the subject of the formula, we have F all over Young modulus multiplied by area. So change in length becomes force times F original length all over Young modulus times cross-sectional area. So which is, of course, F L naught all over E. Now, what is the implication of this? Now, this deformation means if you're using a material, Young modulus depends entirely on the nature of the material. So, for instance, steel has a Young modulus of times 10, 9 Newton meter square, which is 2 times 10, 11. So the Young modulus is very high. So if you want to use a material to build anything, you want the deformation to be too small. So you have to use a material of high Young modulus or high elastic modulus. So materials of high elastic modulus are materials that are not prone to deformation. That is the interpretation of this. Now again, a material of large surface area is also not prone to deformation, because when the area is high, deformation is small. Now, if you want to deform a material, you apply a very high force. Again, if you want to have high elongation or light elongation, for instance, a material of length L and another material of length L1 will produce higher change in length, meaning longer material produce longer deformation than shorter materials. Okay. If we go back to Hooke's law, we see that F equals K multiplied by change in length. Change in length is this. So if we substitute it there, we have K. Change in length is okay. If we make F, sorry that formula, we have change in length equals, the solution I was trying to make is not wrong, but it will not help my interpretation. So F becomes change in length multiplied by AE all over L naught. Okay? Now, if you compare, which is L AE over L naught multiplied by change in length. So, see, if you compare equation 1 and 2, we see that they are similar. So K, constant of proportionality, becomes L multiplied by your modulus multiplied by A all over original length. So in terms of Young modulus, whose law becomes LEA L naught multiplied by change in length. This is what it is. Now, that is elastic modulus. Now, if you have material, we just dealt with a material of a certain length, not considered volt. But if you have a material, say a ball, a material that is spherical, and you apply forces equally on it, say F. Now, you are compressing this material. So we are trying to look at the resistance this material will offer to this compression. It is called bulk modulus. To the resistance offered by this material to which these forces, these equal forces, have been applied. Now, you recall, I agree with me that it will produce, this is V naught, initial volume. The forces, the compressive forces will now reduce the volume of this to a smaller volume. So change in volume will now be V minus V naught, which is minus change, small V minus change in V. So it is negative because initial length is greater than final length as a result of the force that has been applied. Now, we define bulk modulus as denoted by B as bulk stress over bulk strain. So bulk strain is change in volume over volume. This is bulk stress, which is force per unit area, divided by bulk strain equals change in volume all over original volume. And so what it is minor because final volume is greater than initial volume is greater than final volume. Change in V all over V naught. That gives us F over A multiplied by V naught over change in volume. Now, that means B equals F over V naught all over change in V. Now, if the applied force, of course, we know that pressure equals force per unit area. So we could just replace this. Let's say when we're talking about liquids, talking about pressure, we could just replace force over volume by P, pressure, P V naught all over change in V. Okay? I can just neglect the naught since it's only V. Or have P V all over change in V. Now, this is what we call bulk modulus. It's minus, minus because initial volume is greater than final volume. Now, if the applied force produces a change in the area, pressure will have B equals change in pressure multiplied by V all over change in V. Okay? You know what I mean? So this one, if the change is constant, it becomes minus the P all over the V. So it becomes minus V dP all over the V. Bulk. This is bulk modulus. Now we define if the reciprocal 1 over B is called compressibility, because you have dV minus dV all over V dP. It is called at constant temperature. Of course, we assume that this thing is the condition under which the forces are applied to that spherical body is that the temperature will be kept constant. Because if you increase the constant, the molecules of the solid will acquire heat and expand on their own. They will resist the compression. So the temperature is constant. So we have this is called compressibility. Compressibility of the material. It's negative. Now, we have defined Hooke's law, we have defined elastic modulus, we have defined bulk modulus, and we have defined compressibility. Now, both young modulus and compressibility, you will see some people writing it as K. Is 1 over bulk modulus equals that. Now, if I can check how volume grows from this equation. I can have that. I can minus dP over VdP equals K, compressibility. Okay, so I can have I have minus dV over V equals K dP. I can have dV V equals minus K dP. I can integrate both sides of the equation. If I do that, I will have log of V equals minus Kp plus constant of integration C. So if P is 0, C becomes in 0. Okay? So I have, if I solve now, we'll have and I put it back, I put what C is in that equation. I have mv equals minus Kp plus mv naught. So I will have mv minus v naught, mv naught equals minus Kp. Okay? Since we are subtracting, that means they are divided. Since their logs are subtracting, they are divided. I have in v over v naught equals minus Kp. Okay? So we finally have v over v naught equals the exponential of the natural logarithm. So v becomes v naught minus Kp. So you see, so v decreases with the product of compressibility and that of pressure. Okay, so that if you scale that in a graph, it will give you, that is decay. It will give you this from V0 to the maximum volume, it decays, but it will never get to 0. So this is V equals V0 Kp. Okay? Kp. So I hope this helps. In our subsequent classes, we'll solve some problems relating to Hooke's law, elastic modulus and bulk modulus, and compressibility. Thank you. Don't forget to follow us. God bless you.